the last part of the course, we're going to talk about reasoning under uncertainty. So here's a nice quote from Steven Pinker about how the mind works. I suggest you pause it and then read it. So what we're going to do here is we're going to talk about formalizing common sense, right? So this is what the founders of probability assumed they were doing. So what we're going to do now is just going to formalize common sense. Okay, so that's what we're going to try and do here in probability theory. Okay, so what we have now is, so the end of the class, we should be able to justify the use of semantics, know how to compute marginals and apply Bayes' theorem. Later in the week, we're going to talk about how to identify conditional independence, build a belief network domain, predict the inferences, and explain the predictions. That's what our learning objectives for this week are. Okay, here's the assumption. Agents don't have complete knowledge of the world. So you don't know everything that's true in the world. And that's most common, so assuming that we know what the world's like is a bad assumption. However, we need to make informed decisions given your uncertainty. So agents still need to make decisions even though they don't know what the world's like. It isn't enough to assume what the world's like. And so my favorite example is wearing a seatbelt, right? We wear a seatbelt in case there's going to be an accident. However, if we knew we were going to have an accident, then we wouldn't go out and we wouldn't wear a seatbelt. If we knew we weren't going to have an accident, we wouldn't need to wear a seatbelt. However, the reason we wear a seatbelt is because we don't know whether we're going to have an accident. And wearing a seatbelt has a low cost but a high expected value if we have an accident. So because we don't know whether we're going to have an accident, we're going to wear a seatbelt. So we end up with quite qualitatively different things we're going to do when we don't assume we know what the world's like. We don't assume that the world's fully observable or the domain is stochastic. So an agent, we actually need to reason about its uncertainty. We can't just sort of make an assumption about what the world's like. That doesn't work. That turns out to be a very bad way to reason. And when an agent's making an action under uncertainty, it's gambling, right? So whenever you try to cross the road, you're gambling. And that's gambling leads us to probability because probability is the calculus of gambling. Okay, so that's what we're going to end up here. We're going to end up with probability. Okay, so many of you may know about probability, and for those who do, it's going to be a survey. For those who don't, we're talking about subjective probability. It's an agent's measure of belief in the proposition. So that's what we're going to reason about in here. So what's called subjective probability. So it's a measure of belief. An agent's belief depends on its prior beliefs on what it has observed. So what you believe before you start and what you actually observed about the world. If you talk about a particular bird, whether it's going to fly or not, right? Different agents, different people may have different probabilities, right? And our belief depends on what you know about the bird, whether you know whether it's sick or old or the particular bird or the type of bird or all sorts of things. So different people can have different probabilities. So it's not a property of the object, it's a property of our belief in it. So that's what we're going to model as a model of belief. Okay, so the syntax we're going to use, we're going to talk about random variables, and it's essentially going to be the same that we used in constraint satisfaction problems. So syntactically, we're going to start them with uppercase, and we're going to use the term the domain as a set of values that x can reach. Sometimes people use the term range or frame or possible values. There's lots of terms that people use for the domain of a random variable. We're going to use the word domain. And we're going to have a tuple of random variables. We're often going to write x1 to xn as a tuple of random variables, and it has the domain, which is the cross product of all of them. So there's a value for each of x1 to xn. Okay, and often we're just going to write it without the parentheses. We're just going to write it as x1 to xn. Okay, an assignment, we're going to write x equals x means x has value x. So we're going to talk about we're going to write big X equals x. We're going to say x is the variable and little x is going to be the value. And then a proposition, we're going to talk about proposition. It's a Boolean formula made from, so it's made from and, or, and not, and implies and other Boolean operators, logical formulae, made from assignments of values to variables or inequality. We could talk about x is less than y, or the height of someone is less than 1.75 meters. All right, so it's values to variables or inequality between variables and values. Okay, so here's what we're going to mean. Here's the semantics of what we're going to mean. So we talk about possible worlds, specifies an assignment of one value to each random variable. We saw this before in constraint satisfaction problems. So that's a possible world. And a random variable is just a function from possible worlds into the domain of the random variable. Okay, so that's what we're going to mean by random variable. It just takes a possible world and returns a value. We're going to write this funny turnstile signal. We're going to use this funny turnstile signal. It's going to mean that that big X has value little x in world W. So this is our syntax for that. So that's a funny symbol there that means has value in world. And the logic, we're going to use the logical connectives. We use and, or, and not. That's what you'd expect to do. So this alpha and beta is true in a world if both alpha and beta are true. The symbol alpha or beta is true if alpha is true in world or beta is true in world. Alpha is true in not alpha is true in world W if if alpha is not true in W. So not alpha is true if alpha is not true. And we're going to let sigma be the set of all possible worlds. So it's just a bit of notation. We just have a whole lot of possible worlds and random variables to specify what's propositions that are true or not. Okay, so here's the complete best definition of probability. We have a function from a set of worlds. So mu takes a set of worlds into the non-negative real numbers. So we're only going to deal positive numbers. And first one we have is that the measure of the set of all possible worlds is 1. So remember, sigma is all possible worlds. Sigma is all worlds. Okay. And this one here, and the second rule here says that if S1 and S2 have no values in common, so they're sets of possible worlds that have no elements in common, then we can add them. Okay. So it turns out this is all we need to define probability. So the measure, this is called the probability measure of two worlds. If they're disjoint, you can just add them together. If they're not disjoint, this is not applicable. Okay, and then the probability of some formula alpha is just the measure of all the worlds where alpha is true. So it's just the measure of the set of worlds where alpha is true. So that's what we're going to mean in here. We'll give some examples in a second. All right, so here is this. So suppose here there are 10 possible worlds with all the shapes in here. So each of these shapes is a possible world. I'm going to suppose the measure of each singleton world is 0.1. So each of these, for the moment, we're going to assume has a measure of 0.1. So the probability of circle, well, what's the probability of circle? Well, it's 1, 2, 3, 4, 5 out of 10, right, equals 0.5. So it's just 5 out of the 10. Circle is true in circle is true in 5 of these cases, and that's what it's going to be here. Okay, what's the probability of star? Well, it's 1, 2, 3 out of 10, right? It's 3 out of 10, 3/10 of them, or 0.3. The probability of orange is 4/10, 0.4, right? The probability of orange and star, well, orange and star, there's 2 orange stars, so it's 2/10. Okay, that's what's going on here. Okay, the probability of orange and circle, well, it's only 1/10. Okay, there's 1 out of the 10 is orange and circle. Okay, note that the probability of alpha and beta is not a function of the probability of alpha and the probability of beta. There are some constraints on it. You can't just compute it from one or the other. In particular, we notice that the probability of circle is more likely than star, but the probability of orange and circle is less likely than the probability of orange and star. Okay, so you just can't compute it from those things. So you can't just do and, doesn't have a nice formulation. Okay, so it turns out we can actually talk about instead of defining in possible worlds, we can define in terms of probabilities. So these axioms, so for any proposition A, it's greater than or equal to 0. The probability of the proposition true is 1, because true is the set, will end up being the set of all worlds, because true is true in all of them. And the probability of A or B is the probability of A plus the probability of B, if they both can't be true. And it turns out these two, the semantics that we gave, exactly correspond to these semantics, at least for the finite case. Okay. All right, so that's what probability is about. The next part we need to do is what's called conditioning. So conditioning tells us how to revise beliefs based on new information. Remember, probability was a measure of belief. So now we're going to revise our belief as we get new information. So what we're going to do is an agent is going to build a probabilistic model taking all background information into account. This is what's called a prior probability. And then every subsequent piece of information you're going to condition on. And so what we're conditioning on is what's called evidence. So if evidence E is a set of all information obtained subsequently, so after we have the prior, we're going to use this what's called the conditional probability of, so we're going to use this notation, the probability of H given E. So this is called the conditional probability. E is our evidence, it's what we've observed about the world, it's our evidence about the world, and H is a hypothesis, and this gives what's called the posterior probability of H after we've observed E. So here's what we've observed, and H is what we're interested in, and that's what we're going to do, this conditional probability. All right, so let's go through now about what this actually means. So essentially, once we've observed some evidence, we know that some possible worlds are impossible. So all we're going to do is we're going to rule out the possible worlds that are incompatible with our evidence. We're only going to consider the remaining evidence. And some evidence E, we're going to get this new measure. So this one here is going to be a new measure. It's going to follow all the rules of a measure we saw before. So it's going to be a measure, so it's going to have all the same rules that we had before over possible worlds. In particular, the measure of all of the worlds is going to be equal to 1. So let's define this measure of this S, remember, as a set of possible worlds, and we have mu of E of S. So let's look at a few cases here. Let's look at all the worlds if E is false in all the worlds. So this says E is false in all the worlds in S. Right, we've observed E, and it's false in all the worlds, so none of the worlds of S. So what we're going to do there is they must be impossible. So we're going to give those 0. Okay. Now let's look at all the worlds that we don't have it. Well, we're just going to, so if all the worlds, these are all the worlds, this is a set where E is true for all of them. So this is the set of worlds. So this is, if S is a set of worlds, such that E is true in all of those worlds, then we're going to use this value here. Okay, we're just going to multiply them by a constant. Well, because the set of all the worlds, because the set of the mu of E of all the worlds must sum to 1, we can show that the constant is actually equal to probability of 1 over the probability of E. So now we can define the conditional probability of H given E. It's going to be just the measure in this, the measure of the worlds where H is true in this new measure, with this new measure of mu of E, where we've effectively, all the worlds where E is false, we now have probability 0 and the others are multiplied by a constant. And that constant is 1 over the probability of E, and then we can show it's the probability of H and E divided by the probability of E. So this is probably the form that you've seen it before, probably the definition you've seen it before, but sometimes this is a useful way to think about it. It's useful to think about it in terms of just ruling out all the possible worlds where the evidence is false and just multiplying everything else by a constant, because often in our programs that's what we're going to end up doing. It also lets us know why this is the formula. So this is not an arbitrary magical definition, but rather it's a consequence of how we're going to do things. All right, so here's the possible worlds. So we can think about these as the same 10 possible worlds here we had before. If we observe the color is orange, then what happens is we're just going to look at these 4 possible worlds here. So all of these end up with probability 0 because they're not orange. And these going to do it, we're going to multiply the constant here is going to be 4/10 in here. So these is going to be worth 0.25. Okay, so the probability of star, the shape is star, given color is orange, is 2 out of the 4, which is 0.5. Okay, so that's the shape is star, given the color is orange, is 0.5, and the probability shape is circle, given color is orange, is 0.25, right? Because it's 1 out of 4 is a circle. So that's all we're doing in conditioning. All right, so we can actually, so if we have these probability of all of these worlds, we can compute lots of these values here. So for example, the probability of flu and sneeze is we want all of the values, all the worlds that are true, have flu and sneeze true, which are these two. I'm going to sum them up. We're going to add them together, and we're going to get this, right? Flu and not sneeze is these, right? The probability of flu is all 4 of these, so it's the top 4 of these. So we're going to sum the top 4, right? And the probability of sneeze and flu is A divided by C here. Okay, so you can do the rest of it, but once we have that definition, we can compute all of these conditional probabilities in given this set of values. So that's all we needed was those simple definitions that we've seen before. All right, so let's look at a few properties that we need to reason about. So first of all, there's condition. So the rule of conditioning told us the probability of H and E is the probability of H given E divided times the probability of E. Before we had it the other way around, so we had the probability of H given E is this divided by the probability of E. We're going to write it this way. Okay. So what we're going to do is we're going to look at this conjunction of a whole lot of these formulae. And what we're going to do is we're going to essentially just treat this as our new E, and we're going to apply this formula. So it's going to be, so if we treat this as the E and this is H in that formula, then we end up doing this. So remember, this was H, and this is, the probability F given F1 to Fn times the probability of Fn minus 1 to F1. Okay. And so now we're going to do it again to this form. We're going to repeat the same thing to this formula, and we end up with the probability of, well, this is just a repeat of this, and this is just applying this formula again. And if we keep doing that over and over again, we'll end up noticing that it's f of n given all the predecessors times f of n minus 1 given all the ones before times f of 3 given f of 2 and f of 1 times f of 2 times f of 1 times the probability of f of 1. So what we're going to write that down is going to write the product from I is 1 to n of the probability of fi given all of the predecessors. So this is called the chain rule of probability theory. So it reduces a conjunction into a product, but it's the product of conditional probabilities. Okay, that's called the chain rule. We're going to use that a lot. So the chain rule, so now we're going to use some properties of logic, named the probability of H given and E is equivalent to E and H. So these two are the same formula. So H and E is the same as E and H. So now we can write, this is our previous formula, the probability of H and E. It's the probability of H given E times the probability of E, but it's also equal to E and H. So it's also equal to the probability of E given H times the probability of H. Okay. So all I've done there is just change the order of H and E. And now we can divide both right-hand sides by the probability of E. So we're going to see this right-hand side, we're going to divide it by this value. We're going to divide both sides of this by this value. So we get the probability of H of E is the probability of E given H times the probability of H divided by the probability of E. This is called Bayes' theorem. Okay, so Bayes' theorem is going to be very important for what we're doing. It just as a logical consequence of the meaning of conditioning. Okay, so why is it interesting? Well, it's interesting because often we just have causal knowledge. We have things like the probability of a symptom given a disease, right? So given this disease, what symptoms does it have? And what we'd like to do is do evidential reasoning. We'd like to, if someone comes in with symptoms, we'd like to know what disease they have. Bayes' rule tells us how to do this. Often we might have a model about saying in the world status of light switches and switch positions in the house wiring system, and you might know the probability of the light is off. And what we want to do is you might want to say what's broken given what's the problem given the light is off and given the switch positions. I mean, maybe it's normal, but maybe we can show that something might be broken. We might have determined how fires affect alarms, and what we'd like to do is give an alarm to know the likelihood of fire. And we might have a model, like a graphics model, there's a tree in front of a car, and then we can draw an image, so the image would look like this if there's a tree in front, given there's a tree in front of a car, the image looks like this. We know there's probability distribution of what images look like, but what we want to do is we're given an image, we'd like to know what the description is. So it's going to be used for all of these things. Okay, so that's basic probability in a short summary of what we're doing. So that's all we need to know about probability. That's all really there is to do about probability that we're going to do. The only other tool we'll need is a notion of independence. Okay, let's stop here.